My name is Erick. I will present you this research. We compare the pattern of light that we can see to visible light, and we take this model to apply to 6 MeV X-rays that we use it in radiosurgery. Then, okay, the co-authors, they are Werner Chanta, he is medical physicist, and Julio Valls, who is a physicist. The fresnel-franunhofer diffraction, we know this in optics. We have a light of source of light, and when this light passes through a hole, we expected this shape, but we don't forget that the light is an electromagnetic wave, and this works is explained by Maxwell equation. Then, what is observed? Really, we have the object. We wait one profile like this, but the wave observed is like this. We have many concentric rings, one disk and another concentric rings, named Iridix disk. Then, Fresnel-Franunhofer profile is explained in terms of the vessel series. And when one wave passes through the hole, we can consider many sources of this wave that have one diffraction pattern into another place. Then Fresnel-Franunhofer explained in terms the electric field in terms of this integral for any point p sub 0. Okay, but don't forget that the light is an electromagnetic field, and if we know the electric field, we can know the magnetic field using the in Faraday induction law. For this reason is that we work for electric field just, and we can have the magnetic field also. The vessel series is used to approximate this profile, the profile obtained by the light passing through the hole, and the vessel series is a solution of the wave equation in spherical coordinates that we know. Then the vessel series that explain this profile is like this equation. And if we fix the end volume, we can have the vessel series of first kins, zero kins, first kins, second kins to n kins. Then this is the graph of a vessel series, and the radiance of a circular hole like I mostrad is, we can write in terms of the first kin vessel series. And this research born for these two images. Here in top, we have the image of the light, visible light, and we have when we have 4 sources of light, we can see a pattern like this. But if the sources are together, we have diffraction patterns, and we can't differentiate between these two sources. And if the sources are more close, are more together, we can differentiate between these two sources, and this another is very, very close. Okay, this is it for light. What do we have with X-rays? With X-rays, if the sources of X-rays are separately, we have one pattern like, or one isodose lines like this pattern of light. If the sources are more closely are together, we have one pattern like this to visible light. And if we have more together, more close the sources, we have one pattern like this for light. Then we asked why we can use this model to the X-rays when then we work the radiosurgery. Radiosurgery is a radiotherapy technique, and in this technique we apply to the patient high dose of radiation to a small target in one fraction, and we have a high dose gradient. We have a lesion in this region of the brain. Is small, but it's very close to the sternum. Then we need to use small fields. A small field, we consider one small field if the dimension is comparative to the length of shaded particles equilibrium when we have a ionization radiation, or if we observe source occlusion, or if the field size is compared with the size of the detector. Here we have one profile, a lateral profile for X-rays for a large field, but when we have one small field, we can have a source occlusion. Then we work on this tile of the fields. The lateral profile of a large field we can show here, and this is for a small field. We obtain these profiles on a linear accelerator, and we use the automatic phantom. The collimators that we used are of diameter 9 millimeters, 12 millimeters, 15 millimeters, and we can read each millimeter that we use in the output of the linear accelerator. And here you can show that the ionization chamber that is here is moving in lateral. The X-rays are on this direction, and we are mapping the X-rays in this direction, lateral direction, and in different depths. Then the lateral profiles of tiny, like the anterior, like this of this technique for X-rays, is the profile of tiny is like this, and the profile of the light passing through a hole is like this. Then they are similar, and we have the hypothesis. Then it is possible to calculate a vessel series to fit the lateral profile for 6 MB X-ray field. We know that the vessel series are used for a fresnel-franunhofer model, and they explain for light, and we take this universal method to X-rays. Then we propose the polynomial, this polynomial in terms of the vessel series for the irradiance, and we shift X is the lateral movement or lateral position for every different points. When we use the polynomial, we use Python to simulate and for determine the Bessel coefficients. And if we use just one term of the polynomial, we don't have a very good correlation, but if we use three Bessel coefficient, we have good correlations, and this is for 7 millimeters diameters of the collimators and 100 millimeters of depth. We have to 10 millimeters of diameters. The data measured and the adjustment model are they has a good correlation. They have a good correlation, and our conclusion is in first approximation is possible to use Bessel series proposed by fresnel-franunhofer model to obtain lateral profiles of X-ray beam of 6 MV. And this is important because we have one universal method to approximate the reference that we use. I want to acknowledge to the organizers of these webinars, in special to Rosalind, to Dr. Miguel Ángel Ortega, who is the medical director of this clinic that I work, the authorities of San Carlos University of Engineering Faculty. Some about me: I'm the vice president of Latin American Association of Medical Physicists, coordinator of National Commission of Medical Physicists. I am a medical physicist. I am physics teacher, and my contact if someone want to write me. And Guatemala waits for you. When you want to come, you can write me. I am very happy to have you here.